Section 3.2, the growth of functions. The time required for an algorithm to terminate depends on the size n of the input data. The time also may depend on the structure of the data. The minimum time needed to execute the algorithm among all inputs of size n is called the best case time for size n, and the maximum time needed to execute the algorithm among all inputs of size n is called the worst case time for size n, and similarly we can define the average case time for size n. Usually we are interested in the worst case time for size n. The running time of an algorithm for a given data depends also on the particular computer where the algorithm is executed. If we take a computer which is 2 times faster, then we expect that the running time will decrease 2 times. But this does not help much if the original time was large, say 2 million years. We want to compare the performance of algorithms when the size n of the input data increases indefinitely. For that reason, we need to be able to compare functions of n when n approaches infinity. The running time of an algorithm may be a very complicated function of n. We want to compare that function with certain simple and familiar functions. We use these definitions. Let z plus be the set of all positive integers and f and g be functions from z plus to r. We write f of n is equal to b cos g of n and say that f is big O of g. If there exists a positive constant C1 such that the absolute value of fn is less than or equal to C1 times the absolute value of g of n for all but finitely many positive integers n, which is the same as saying that this inequality holds for all sufficiently large values of n. Similarly, we define f of n equals big omega of g of n. If there is a constant, positive constant C2, such that C2 times the absolute value of g of n is less than or equal to the absolute value of f of n for all sufficiently large values of n. We write f of n is equal to big theta of g of n if f of n is equal to big O of g of n and if f of n is equal to big omega of g of n. That is, if we have this inequality for all sufficiently large values of n. We will not use these definitions. Instead, we will use some properties of big theta notation that can be proved with these definitions. And we'll want to compare the growth of functions with functions from this table. Constant, logarithmic, linear, rhythmic, n times logarithm of n, polynomial, n to the b, where b is a given positive constant, exponential, b to the n, where b is greater than 1, and factorial. For large values of n, we have this ordering. The fastest growing function is n factorial, then b to the n, and so on. And the constant function is, of course, the least growing. The following properties can be proved using the definitions that we presented above. If P of n is a polynomial in n of degree k, then P of n is equal to theta of n to the k. The leading term determines the growth. For example, this polynomial is equal to theta of n cubed. What is the theta notation for 6n plus 1 squared? We can multiply out, then we have a polynomial of degree 2, so it has theta notation, theta n squared. The second property, if f1 is theta of g1, and f2 is theta of g2, and g1 is greater than g2 for all sufficiently large values of n, then f1 plus f2 is equal to theta of g1. That is, the largest growth dominates the sum. For example, if f1 is theta of n squared and f2 is theta n logarithm of n, then f1 plus f2 will be theta of n squared because n squared grows faster than n logarithm of n. In this problem, select theta notation for this function. 3n squared is equal to theta n squared. 2 n logarithm of n is equal to theta n logarithm of n. The constant doesn't matter, constant factor doesn't matter according to our definitions. And because n squared grows faster than n logarithm of n, the sum will have growth theta n squared. Third property, if f1 is theta of g1 and f2 is theta of g2, Then f1, f2 is theta of g1, g2, and if f2 and g2 are different from 0 for all sufficiently large values of n, then f1 over f2 is theta of g1 over g2. Again, this property can be proved using the definition, but we are not giving the proof, we just apply the property. If we have to estimate such a quotient, we can use this property. N plus 2 is theta of n because this is a polynomial. This is also a polynomial, so it is equal to theta of n squared. Then the quotient is theta of n squared over n, which is theta of n. Property number 4, if f of n is this sum of the first n positive integers, then f of n is theta of n squared. We can prove this easily because this sum is equal to this polynomial, and the polynomial has big theta estimate given from the leading term. Problem 7. Select theta notation for this sum. This sum can be written this way, just factor out a 2, then it is 2 theta of n squared, and a constant factor can be ignored. So the function is just theta of n squared. 5, property 5, it can be shown that the kth powers of the sum of the kth powers of the first n positive integers is equal to theta of n to the power k plus 1. And logarithm of n's factorial is theta notation and logarithm of n. This is without proof. We are not considering the proof on this.